All right, welcome everybody. Welcome to another session in the course. Today we're going to cover the complexity theory. We're going to focus on the parts that we're going to need in our programming practices. So we're not going to get a lot into the details of this very large theory, but we're going to learn the parts that we most need to make efficient algorithms. So what is the complexity theory? The complexity theory basically is just a function, just like a mathematical function, that relates the input to the output, the size of the input to the number of steps required to compute or perform the function, okay, or to execute. So there's two types of complexity. There's the time complexity. So it's the time complexity, and there's also the space complexity. Now, both of these are talking about complexity. Basically, they relate the amount of resources required by an algorithm in order to do its task. Now, for the time complexity, the resource is the time, how much time it is required, and for the space complexity, the resource required is basically the memory, okay, the memory inside the RAM. Now, we can say that an algorithm is efficient if and only if the function, the complexity function is small. So to make efficient algorithms, make algorithms whose complexities are small, okay, whose complexities functions are small, okay. We express that complexity with a notation called the big O notation, the big O notation. So let's say we have an algorithm called T of size n. We can say that the complexity of this algorithm equals O, that's a big O, and we give it a polynomial or any expression, any function. Let's say a function g of x. So the complexity of the algorithm T is g of x, that's g, okay? So the complexity of T is g of n. For example, we can find complexities such as order 1. 1 is a polynomial. So we can find another complexity, order, the O stands for order. So we can find complexities such as order n. We can find order n squared. We can find order n cubed. That's cubed. We can find complexities like order n times any constant. We can find complexities such as order n times log n, so that's n to the k times log n to the c, so that's n times any constant times log n times any constant again. Well, we can just get rid of that constant. There are also complexities such as some constant to the power of n, okay? So that's, we call them non-polynomial functions, exponential functions. There's also factorial, so that's n factorial. So basically there are a lot of forms of complexities, but these are the most popular and widely spread ones. So I'm going to start by examples, because examples are really helpful to make this, to build the intuitive part about this course. So let's say we have an algorithm that, given an array, our algorithm will basically print all the numbers of an array of size n. So let's write this algorithm. It'll be something like this. So for I starts at 0 up to n, for every cell, so we're just going to print it. So print, let's say this array is called t, so print t of I. And that's AND for. So how many steps will this algorithm take in order to print the entire array? Well, if the array size is 10, then this would take 10 steps. If it is 100, it'll take 100 steps. If it is 1 billion, it'll take 1 billion steps. So the number of steps required really depends on n. Okay? So the complexity of this part of code here, this pseudocode, this little algorithm, is order n. The amount of time required to print all the numbers of the array is the same as the number n. So if n is 100, then this will take 100 units of time in order to print all the numbers. Okay? So let's take another example. Let's say we have an array, again, of size n, that has a bunch of numbers. And these numbers are random, they're not sorted. Now let's say we want to look for a specific number. Let's say we're looking for the number 4. So let's write an algorithm that does that. So our algorithm would be something like this. So we have a counter, I, starts at the first index, 0. We would say while I is less than n, and t of I is different. So again, this array is called t. So t of I is different to the number that we're looking for. Let's say it's c. So t of I is different to c. We're basically going to increment I. So I plus plus. So once we reach the end, or we find our number, then we're going to quit, right? So after we quit, we're going to add an if statement here. So if I is less than n, it means that we found our number inside the array. Okay? Otherwise, we've reached the end of the array, but we didn't find our number. So we're going to print, we found the number at index I. Okay? Otherwise, we're going to print we did not find the number. So basically this is a basic algorithm that will iterate through the array, and when it finds our number, then it'll tell us where it found the number. Otherwise, it'll say we did not find the number. So what is the complexity of this algorithm? Well, whenever we deal with complexity, there's 3 types of complexities. There's what we call the worst case complexity. There's the average case complexity, and there's the best case complexity. So best case complexity. Basically, whenever we talk about the complexity of algorithm without mentioning which type of complexity we're talking about, then we assume that we're talking about the worst case, okay? We always care about the worst case. What is the worst case of an algorithm, okay? So the complexity of the worst case here is n. Why n? Well, what is the worst case? The worst case is that we keep incrementing our counter, we keep moving it to the right, searching until we reach the end of the array and we did not find our number, or maybe we find the last element, which took us an entire n operation to find our number, right? So the worst case of this while loop here would be n, so that's order n. We would have to traverse the entire array to find our number, or maybe not to find it. But we have to traverse the entire array. So the worst case would be order n. It takes n operations in order to find our number. And what is the best case complexity? Well, the best case complexity is minimum number of steps required to find what we're looking for. What is, if we're so lucky, what is the best case? Well, the best case is that we find our number at the very first index. Let's say, for example, we're looking for the number 1. And luckily, 1 happens to be at the very beginning of the array. Well, in that scenario, we're not going to continue this loop. We're just going to quit, okay? So we're gonna say while I is less than n, yes, 0 is less than n, and t of I is different to c. No, it is not different. We found our number, we quit. So this while loop took only one operation, and then this if statement only took one operation. And yeah, so the overall best complexity, the best complexity is order 1. It's a constant time, okay? Cool. And there's also the average case complexity. Well, the average case complexity means on average. Like we do this, we search for a bunch of numbers a variety of times, like 10, 20 times, and then we take the average case. What is the complexity of the average case, okay? So usually we do not care about the average case. We only care about the worst case. But for the average case, there's one very important example where the average case is really, really efficient to know. It's really important to know. In the example of the quicksort. Because quicksort has a worst case complexity order n squared, which is very large, and an average case complexity order n log n. But this algorithm, most of the time, it works with order n log n. So the average case is more truthful. It's most truthful than the worst case. Okay, so we cannot count on the worst case because it doesn't happen very often. Cool. Now I'm going to list the most popular complexities and give you a bunch of examples of where you could find any one of them. And then we're gonna start doing a couple of examples to make sure that you get the idea. So let's try this in red. Let's change the color. So list of popular complexities. Now we have the first complexity is order 1. Order 1 is a set of all complexities that are basically take a constant time operation to perform. In other words, the time required to perform such operation does not depend on n. Okay, so let's say, for example, you have two numbers. Let's say you have x that has a number and y that has a number. And you want to swap these numbers so that y takes the content of x and x takes the content of y. So basically to do that, we could create a temporary variable, and inside this temporary variable we put the content of x, and then x takes the content of y, and then y takes the content of that temporary variable. So these three instructions would swap the content of x and y. So if y had 6 and x had 7, we would end up with y having 7 and x having 6. Now, whether x is 7, 9, 20, 1,000, a million, a billion, it doesn't matter. We're going to always execute 3 and only 3 instructions. So the time required to perform these 3 operations doesn't depend really on x nor y. It is only 3 instructions, so the complexity is constant. For that reason, we say that this will take a constant time. So that's order 3, which is equals order 1 because, well, we can take the 3 out. So this is constant. Constant is order 1. Okay? Now, all the operations like x takes y plus z and maybe x takes 4 and all these constant operations really require a constant time. Okay? So their complexity is order 1. All right, let's open this again. All right.